Welcome back. After about a month, we are starting a new topic, that is unified performance-based design for frame-shear wall building. The direct displacement-based design for frame-shear wall building we had taken up earlier, and that had some limitation that we shall again focus. So direct displacement design for frame-shear wall building could satisfy only drift as the target performance criterion. But the damage level which is given by the performance level could not be captured, could not be accommodated in the design in the DDBD method for frame-shear wall system. The system also did not give us the wall size, the length of the wall, thickness of the wall. So that was to be found out through iterations. Iterations means more time, but in the UPBD method for the same system, we can overcome all the limitations. The UPBD method can design for drift and performance level together, and not only that, it gives the sizes of the wall in the beginning of the design so that iterations are avoided. Let us see just recapitulate our memory regarding the shear wall. So this is a shear wall here, and the shear wall, and rest are frames. The beam elements and the column elements are the frame elements. In the cross section, you can see the red colors are the vertically running steel, and there will be also horizontally running steel. We'll see in the next slides. Here is a model for a shear wall building. These yellow colors are shear walls. In the corners, they are like touching at a 90 degree, and there can be shear wall also in between. At the central part, the core part, there can be shear wall for lift, etc. The reinforcement details for a typical shear wall is shown here. You have the vertically running steel and you have the horizontally running steel. At the two ends of the shear wall, you see what is called the boundary element. Boundary element is not a must, it can be given. If it is given, it increases the ductility and strength of the wall. If it is even not given, then you have to strengthen the end of the wall with extra vertical reinforcement and stirrups. So this is a cross section of the wall. A practical example of shear wall, these are the shear wall running vertically, and there are openings in the shear wall, and rest are frame elements. So it is a frame shear wall building. Let us consider the plan of a frame shear wall building. So earthquake may come along the long direction of the building plan or along the short direction of the building. But suppose it comes along the long direction of the building plan, then where do we place the shear wall? So in that case, you have to put the shear wall like this. The shear walls are to be in the same direction as the direction of the earthquake. And shear wall is to be placed symmetrically in the building. So we have put one here, another here, and on the opposite side also in this similar shadow configuration we are putting shear walls. Now if the earthquake comes from the transverse direction of the building plan, then you have to put shear wall here along that direction. So this is the simple way of disposing the shear walls. You must see that it is placed symmetrically about the plan of the building. Here is a cross section of the shear wall. Now shear wall is standing on the base at the bottom, and it is carrying lateral load at the top. So it is just like a cantilever system, fixed at the base and free at the top. It is a cantilever, and the length of the shear wall is this length. This is called the horizontal length, is called the length of the shear wall. Perpendicular to this, which is not shown here, you have the thickness of the shear wall. You have the vertically running steel, which are the flexural steel or cantilever steel, and you have the vertically running steel, which carry the shear. So if you take a cross section AB, cutting this shear wall through some horizontal plane, you get a section like this. So here to here is the LW. So here in the vertical direction, you get the length of the wall LW, and here reinforcement here. So there will be neutral axis here. So this is the location of the neutral axis. Let's say the depth of the neutral axis is X, and at the bottom you have the tension zone. So we take the following symbols: x for depth of neutral axis, LW the length of the shear wall, the horizontal length here to here, MR moment resistance of the shear wall, MD factor design moment, X limiting the limiting depth of neutral axis, AST vertical steel, TW thickness of the shear wall, rho equal to vertical steel ratio given by AST by TW into LW. PU is factored axial load. So before going to the UPBD method, we are trying to understand the Codal method. Why it is? Because let us see what are the problems when we take the Codal method of design. Now, Codal method of design are not very clearly outlined in many codes, but in Indian Code 13920, some hints are given, some formulae are given for calculation of the strength. So we are following IS 13920 for this purpose to get the design of the shear wall. Now we must understand that in this Codal design, the initial sizes are not known and there is no hints for getting the initial sizes. So you take the initial size arbitrarily based maybe on your experience or just by heat and trial. These are the other parameters which are involved in the Codal method. X by LW is the ratio of the neutral axis depth to the vertical section we have taken earlier, which is the length of the wall LW. So this is given by this parameter, then X limiting by LW is given by these parameters. The other symbol used in this formulae are phi is given by 0.87 Fy, rho by FCK. Rho is the steel ratio we have seen in the previous slide. Beta is given by this, lambda is this, and rho we have seen in the previous slide. Now 0.002 is the strain in the steel. This is what is the strain allowed by the code, and 0.87 Fy by S is the real strain given by the steel. 0.87 comes from the factor, partial factor of safety for material, which is 1.15 for steel. Reciprocal of 1.15 is 0.87, and 0.0035 is the maximum strain in the concrete that is allowed in the Indian code. Now how to get the moment of resistance of the wall. Now I tell you the design principle is like this. You take any size of the wall, the length of the wall, thickness of the wall, and you choose the material, and you also choose some percentage steel. Minimum percentage of steel is 0.25%. So that way you can consider a section and some steel, and you have to calculate this X by LW, X limiting by LW values, and see whether they are one is less than the other or one is greater than the other. So when X by LW is less than X limiting by SW, moment of resistance is given by this formula involving all the parameters we have just seen. 0.416 comes from this stress block used in the Indian code, which is parabolic rectangular stress block. When X by LW is greater than X limiting by LW, and it is following this within this limit, both are less than 1, then it is given, the moment of resistance is given by another formula. So if you choose a section, then all the parameters can be calculated. You have chosen the section, you have chosen a steel, so all the parameters can be calculated. You calculate the S by LW, X limiting by LW, and based in the relationship which is greater, you use either this formula or that formula. In this second formula, you see there are parameters like alpha 1, alpha 2, etc., which we can see in the next slide. And in the previous slide, you can see when you are using the formula in the second case. In this second case, it is not X by LW, but it is X star by LW. That is, you are getting a new ratio here, which is other than the ratio we have already discussed, X by LW or X limiting by LW. So it is X star by LW symbol I have given. How to get this ratio X star by LW? It is obtained from this formula, solving this algebraic equation, alpha 1 X star by LW square. alpha 4 x star by LW minus alpha 5 equal to 0. So from the quadratic equation I can solve the result x star by LW. It comes out in terms of the constants minus alpha 4 plus or minus alpha 4 square 4 alpha 1 alpha 5 by divided by twice alpha 1. So you can calculate this and then use it in the formula. Now other values are here. Alpha 1 is given by this expression, alpha 2 is given by this, then alpha 3 which involves this x star by LW. So before calculating alpha 3 you have to calculate this x star by LW from this expression, then alpha 4 and alpha 5. Now shear check, all those parameters we have seen so far are involved in the calculation of the moment of resistance of the given wall. Now the same wall is to be checked for shear also. The average shear stress in this section is given by design shear force BD divided by B into D. B here is the thickness of the wall and D is the effective depth of the beam when you consider it is as a cantilever beam. Then D is given by 0.8 into LW. That is 80% of the length of the wall is considered to be effective in taking shear. So this average shear stress tau B BD by BD should be less than maximum allowable shear stress given in the code. So this maximum shear stress is given in the IS 456. In other course also you will get the corresponding values, maximum shear stress permissible. So first you have to apply this check whether the section you have chosen is viable or not against shear. If it is not satisfied, then you have to increase the size of the wall. Now a part of the shear, which is BD, design shear force, is taken by concrete, which is given by BD into tau C, where tau C is the permissible shear stress in concrete corresponding to the percentage tension steel in this section. And BS is the remaining shear to be taken by the stirrups. So it is given by BD minus BC, you can calculate. So once BS is calculated, the shear taken by steel or stirrup, we can find out its spacing from this formula 0.87 Fy ASB D divided by BS. ASB is the area of all the vertical legs of the stirrup. Generally it will be 2 leg because the shear wall thickness is not very large. Shear wall thickness may vary from say about 150 to 300. So 2 leg will be only possible in the stirrup. So ASB is the area of those legs of the stirrup. You have to consider a diameter of the stirrup and then find out ASB, and other parameters are known. So putting this value of BS here, you can find the spacing of the stirrups. These are horizontal stirrups. Now let us go how it works. So we are making the Codal design through the Excel sheet IS 13920. Latest version is 2016 version. So the parameters that we are taking for design, the factor design moment MD and factor design shear force BD and factor axial load PU. These are the supplied loadings. For this moment shear and axial load, you have to design the wall. So you do not know what should be the length of the wall, thickness of the wall, and what should be the reinforcement, etc. For reinforcement, one hint is given that reinforcement ratio should be 0.25% or more. So I have put all the formulae here as we have discussed in the previous slides. The length of wall you have to assume, thickness of wall you have to assume, concrete strength I have taken at M30, so it is 30 megapascal strength, compressive strength, and corresponding to that tau C max is 3.5 megapascal, you have taken from the IS 456 2000. The yield strength of steel Fy 500 megapascal I have taken, diameter of bar I have taken 20 mm, and number of bars will change of course. Number of bars, so the number of bars or diameter of bars, you can regulate the amount of steel that you are providing, not by design but you are providing. So vertical steel calculation is done here, millimeter square, and ES is the modulus elasticity of the river. Then rho, that parameter we have discussed, then phi, that parameter, beta parameter. This all formula I have written here so that in the calculation we can use it directly. So this formula I put here. For example, the beta, you can see here the formula is already there involving all the relevant parameters. Then lambda value, then x by L, that ratio, and x limiting by LW, that limiting value of that ratio. So it is like that. So in the present case, 1 meter length of the shear wall has been considered and 200 millimeter thickness of the wall. For that, x by LW is coming more than x limiting by LW. So the second formula is to be used. I have used here, shown here first formula, and you can also put the second formula and calculate. So now the moment resistance is obtained from this formula we have discussed. Moment resistance has come out in Newton millimeter this, and in kilonewton meter this much, and we put a logical cell here like this. If this is greater than that, then it is safe, other unsafe. So it is showing you unsafe. Similarly, the shear design, it is showing unsafe. Where it is unsafe? Tau B maximum allowable, tau C max is 3.5, and tau B here it has come 5, so it is unsafe. Okay, and further shear design is given here. Finally, you find you choose the diameter of the stirrup and the spacing. So spacing obtained from this formula here, using this formula, and finally you moderate it and use a practical value. So in the moment of resistance it is unsafe, shear design is unsafe. So what do you change? The number of bars we have to put more perhaps. Let us reduce it 20. Then of course it will be unsafe. Now we increase the length of the shear wall. Say we put 2 meter. So we put here 2. It is in meter. In the corresponding formula you have to convert it to millimeter, because all the parameters are in millimeter. For example, this FCK is in millimeter, FY is in millimeter. So in the formula I have multiplied by 1000 to make all these in millimeter. So I have taken 2 meter now, the length of wall. It is still unsafe in moment. Let us see 2.5 meter. It is still unsafe. So you see that it is not so easy to get a viable size of the wall. It is a hit and run method, hit and trial method. Gradually you have to increase or decrease, and you have to moderate the steel, and finally you may get a safe design. Our task has been made easy by using the Excel sheet. Otherwise it will be very difficult. You can make a C++ program also to carry out all these steps. So 2.5 unsafe, let us make it 3 meter and see. So 3 meter is also unsafe. Why unsafe? Because the moment resistance is 3535, and given bending moment, it is factored value is 8000. Bending moment is factored value, shear force is also factored value, and ultimate load, axial load is also factored value given here. The partial safety factor for load may vary from country to country. In India it is 1.5. So 3 meter is unsafe. Should we change the thickness and see? So it is 0.3 meter. 300 millimeter still it is unsafe. So obviously length is to be increased, and more than 300 millimeter thickness of wall is not desirable because it will be costly in that case. So let us say 3.5 meter and what happens. 3.5 meter also unsafe. Then we have to choose 4 meter. 4 meter is also unsafe. Then 4.5. I am not taking arbitrary very large at a step, because in that case it will not be economical. We have to see the economy also. 4.5 is unsafe. Let us give 5 meter length of the wall. 5 meter is unsafe. 6 meter. 6 meter has become safe. Maybe 5.5 may be safe. Let us see. 5.5 is also safe. So that will be the economical size. It is showing safety in shear check also. Shear check, so it is safe in both way. And this condition is also satisfied. X by LW is less than X limiting by LW here. So basically this formula is valid. Otherwise second formula I can take up and put those cells that we have not put here. So first formula is giving us the all values, and the constants alpha 1, alpha 3, etc. are shown here in formulae, and values I have calculated. Alpha 3 is to be calculated at the end, because alpha 3 requires, alpha 3 is not here. Then how we have calculated the moment of resistance? Because in the first formula, under this condition, alpha 3 is not required. In the second formula, all the alpha values will be required, and alpha 3 also will be required. So if you calculate x star by LW, which is found here, x star by LW, then putting in this formula, you can calculate alpha 3. Alpha 3 will be required for moment of resistance calculation through the second formula when this condition reverses, x limited by LW becomes more than x by LW. Let us now go to the shear design. In the shear design, our factor shear force is 3000 kilonewton, and tau v calculated is 0.6061, which is less than tau c max, so it is all right. Now d equal to 0.8 LW, so d is this much. BC equal to tau c BD, so it is coming 9090 kilonewton. So BS, the remaining shear force to be taken by the steel, is BD minus BC is 2010 kilonewton. Now 2-legged 8 mm stirrup is used, suppose. In that case, here it is taken 10 mm. So if you use, let us take 10 mm. So for 2 leg 10 mm ASB, area of the both legs becomes this much millimeter square. And from this formula, you get the spacing of the stirrups, which is 149.6 millimeter. So we use 2 leg 10 mm stirrup at the rate of 100 millimeter center to center. That will be all right. So this is shear design. Now you see the cumbersome method of design, the step by step you are proceeding, and you are making iteration one by one. Now you see 300 millimeter thickness appears to be large, so let us change it to 0.25, 250 millimeter. In that case also it is safe, so that will be a wiser design. Can we change it to 2 millimeter, 0.2 meter? 0.2 meter. See, it is unsafe now. So 0.25 is all right. 0.25 meter is safe. And number of bars, you see here, diameter we have used 20 and number of bars 20, so there will be a problem now. Your length of shear wall is 5.5 meter, and you are using 20 number of bars. So the bars will be put widely apart from each other. So what to do? We can decrease the diameter, say 16 mm. And from your knowledge, you know lower diameter is better in concrete, which reduces the tendency of cracking. Now it is unsafe because you have used only 20 numbers of bars. So let us make it 30 and see. Still unsafe. So 40. Safe. So 16 mm diameter, 40 numbers of bars. There will be 2 layers of steel. In each layer you will put 20 number of bars. And see the spacing by calculating that it is 5.5 meter minus the clearance at the ends divided by the number of bars per mesh is 20. What is the spacing? If the spacing is very large, then you increase the number of bars. You cannot go below the 16 mm diameter. It will not be wise to use less than 16 mm diameter in shear wall. So you can adjust the number of bars so that the spacing between the vertically running bar is not very large. After all, it is RCC, so mesh is to be complete, mesh is to be actually available. So by this I wanted to show you that the Codal design is not a straightforward design. You require a large number of iterations, and further you get a safe design only with respect to your given factored bending moment and given factored shear force and factored axial load, but you are not getting anything regarding the performance of the system. You cannot predict what should be the drift of the building which has used this wall. You do not know what will be the performance level of that building when it is using this design of the shear wall. So through the Codal design, those are not possible. That's why we need to go to performance-based design, and the better way in the performance-based design is the UPBD method, which takes into account both the drift and performance level. Thank you very much for coming with me up to here. Please like the video and share it. Please subscribe the channel to encourage us and be with me. I shall be coming with the second part of this task very soon because continuity has to be maintained. Thank you.